Welcome back, my dear friends. A very good morning, good afternoon, good evening to all my students. I am Raghunandan Sengupta from IME Department, IIT Kanpur, and this is the second last lecture for this 8-week program for TQM under the NPTEL MOOC series. And as you remember, we were discussing about Kusum charts, which is cumulative sum of charts, then exponential moving charts, and then we discuss later on at the fag end of 30th lecture and also in the 37th lecture that the upper control and the lower control for the exponential charts were basically exponential in the nature that they asymptotically reached a straight and parallel line to the mean value, the central line, which is mu suffix naught. Similarly for LCL, and the values of lambda, which is the weights you want to give for the recent reading and the 1 minus lambda to the past reading, or it can be vice versa also, how you will put the weights, would basically dictate the rate of those particular lines, the upper control and the lower control, basically being asymptotic and being parallel to the central line. And also another thing, interesting thing which I keep repeating time and again, is basically the overall the importance of central limit theorem is so huge that in all the calculations we saw that when you are trying to take basically consider the value of H or L, whatever it, in the long run they would be equally dispersed both on the upper part and the lower part of the central line, such that the semblance of central limit theorem considering equal dispersion would be coming out in all the examples. So, we will consider the inertia effect in exponential moving weighted moving average. So, there is one potential concern about this exponential weighted moving average is basically some small values of lambda. So, lambda, if you remember, is the weights. So, more or less the weights I put on the past data would basically mean that how slow and fast the convergence would occur and how the rate of convergence or rate of change of the upper control and the lower control would happen. So, if the values of exponential weighted moving average is on one side of the central line, when a shift in the mean is in the opposite direction, so it could take this overall method several periods before it basically shifts has a shift in the mean values, because smaller lambda values does not weigh the new data very heavily. So, the new data which is giving us more information, if you are not weighting them, obviously their actual effect would be coming up later on, because we are putting more emphasis on the past data. That means T minus 3, T minus 4, T minus 5 would have more predominance than T minus 2, T minus 1. So, the recent data which is T minus 1 and T minus 2 are not that significant, hence those values would be much more weighted, the past data. So, once the actual level of significance or the level of importance of this recent data slowly goes more into the past, it will be able to have its effect on the present reading. So, that is why lambda values being positive, more high or less high, I will not use the word positive, being high or low would definitely have an effect. How fast or slow, the actual effect of the shifts are discernible to us. So, this is called the inertia effect. Inertia effect, if you remember, even though I am using simple physics, that once the body starts moving, it continues moving until unless stopped, or vice versa or otherwise. So, basically it means that once slowly the change is effective and it is discernible if the values of lambdas are considered accordingly. So, if I continue reading it, this is called the inertia effect. It can reduce the effectiveness of the exponential weighted moving average depending on what the values of lambda is. Obviously, lambda would depend on your past experience, what type of data you have, whether it is 1 year data which is affecting our reading, or it is 1 month data or 1 week data, whatever is there would have a significance in the way we are calculating. And if you remember, I did mention time and again 2 very simple examples: warm clothing, warm clothes with respect to, say for example, the clothes, this refrigerator and cooler sales. So, obviously they would have different time periods, but obviously the greatest effect would basically 1 year down the line, but they can be other type of data also, or other type of reading also, where the effects can be not 1 year, can be, say for example 6 months, can be 1 month, whatever the case may be. We will now consider the concept of signal resistance. Signal resistance of a control charts to be the largest standardized deviation of the sample mean from the target or in control value, not leading to an immediate out of control signal. So, obviously, it will give us the information that the signaling which is happening, that the set of change which is happening are not being reflected in a proper manner to give us actually where the changes are occurring. The word change I am basically meaning the change of the whole process such that there is process capability and the concept of assignable causes, unassignable causes would coming into the effect. So, they are should be discernible, but they are not due to reasons. For a Shewhart chart, the single resistance, signal resistance is basically would be calculated by a multiplying factor using the controlling limits which is there, and this L factor which we also consider, which we saw in exponential weighted moving average, would be coming into the picture for our better calculations. So, if we see for the exponential weighted moving average charts, the signal resistance would be calculated by a factor which basically depends on lambda, preliminary lambda and the L value. So, obviously, lower or higher the values of lambda would basically dictate what is the values of SR, which is signal resistance. Based on that we can do the calculations. And where the W value which is there is basically the required statistic. The statistic is basically from the sample characteristics which I am getting, which will give us some information about the overall general characteristics of the exponential weighted moving average model. Now, one can use the combinations of the exponential weighted moving average and the Shewhart charts also. So, like the CUSUM, which is cumulative sum of charts, the EWMA performs well against small shifts, but does not react to large shifts as quickly as the Shewhart charts. So, Shewhart charts will give us movements in whichever direction, positive or negative, assignable cause being higher or low, whatever it is, as soon as possible. But for small changes, we saw that that exponential weighted moving average performs well. So, obviously, a combination of them would be the best, which we tried to do that once we just finished CUSUM charts. So, those type of concepts are also available, where it becomes much more mathematically intensive, but they can definitely be calculated accordingly. A good way to further improve the sensitivity of the procedure to large shifts without sacrificing the ability to detect small shifts is to combine a Shewhart charts with the exponential weighted moving average. Like the same way, like in the CUSUM charts along with Shewhart charts, the combinations can be done for Shewhart charts along with EWMA, such that both the large and small deviations and shifts can be taken care with equal positive footing. These combined Shewhart EWMA control charts are effective against both large and small shifts, as I just mentioned. When using such schemes, it is helpful to use slightly wider than usual limits on the Shewhart chart, say for example about 3.25 sigma or 3.5 sigma. So, if you remember for that, technically the 3 sigma would be about 99% of coverage, considering again coming back to the central limit theorem concept. So, they would give a better idea, but we will try to basically have a higher level of upper control and lower control, such that both for small shifts and large shifts we are able to entertain and understand the shifts much more precisely than only basically understanding the small shifts or the larger shifts. Obviously, it would mean that we have to sacrifice. So, like all the large shifts, as soon as they are discernible, was applicable for the Shewhart charts, or all the small shifts as soon as they were available was available in the EWMA charts, but you have to compromise in such a way that increasing the so called limits also brings into the picture that we are able to take both the large shifts and the small shifts, but not to that equal proportions as we did in the individual cases, but they are able to take both of them quite nicely. It is also possible to plot both xi or the exponential weighted moving statistics, which is Zi, which is the standard one we discussed, on the same control charts along with the Shewhart's and the EWMA limits. This procedure of using one chart for combining the control procedure that operators quickly become if they are utilized, they very quickly become adept and are able to handle both these concepts on the same charts. When the plots are computer generated, different colors or plotting symbols could be utilized in order to differentiate the control limits both for the EWMA as well as the Shewhart's charts. Now, if somebody wants fast response or fast initial response are wanted, and they are to be a feature of this exponential weighted moving average one, then it is possible to add the fast initial response or head start feature to the EWMA. As with the Kusum charts, the advantage of the procedure would be to more quickly detect a process that is off target at startup. So, obviously if it is off target, so you want initial response to be fast so that you are able to take corrective actions. Two approaches are basically suggested here: set up one-sided EWMA charts and start them off at values midway between the target and the control limit. Another would be use a single control charts, but narrow the time varying limits even further for the first few samples, which means that if you are able to narrow the time limits and are able to take calculations more rapidly, it would mean that we are able to tackle the changes in the shift, or the fast initial responses are done in such a way that the responses which you are going to get would be much more applicable for our case. So using a single control charts but narrow time limits, time varying limits even further for the first few sample points, an exponential decreasing adjustment could be added into that to further narrow the line. So, if you remember that in the case when we did for the exponential one, either the control was upper control was somewhere here, lower control was somewhere here. So, the lower control could go like this, upper control would go like this. So, if there is some changes which are occurring, I will try to. So, if some changes are occurring here and they need to be responded fast in the sense that we want to take corrective action based on the responses we are getting and we are getting the information, then obviously the time varying points should be much more closer, such that the weightages are given accordingly and the responses and the information set based on which one can take corrective actions are available to us as fast as possible. So when you are basically considering this fast response norm, so obviously you will consider the value of the parameters or values f and a accordingly, and the choice of f as 0.5 is attractive because it mimics the 50% head start often used by Kusum charts. Both of these procedures perform very well in reducing the ARL to detect an off target process at the startup. So obviously we want to be aware of the aberrations at the word go. So how we are able to do that, considering those different parameters which are brought into consideration, we are able to do that. The second procedure is easy to implement in practice, but obviously they give us good results. If somebody wants to monitor the variability, so obviously in all these things, if you remember, I have been mentioning time and again, we want to find out the mean value and corresponding to that the upper control and the lower control limit. So if you want to find out the monitoring the variability is important, so we will consider xi to be normally distributed. Again, is a very important point to note, with a certain mean of mu and a certain standard deviation of sigma. The exponential weighted moving mean squared errors would be used. So in this case, we will use the values in such a way where I will try to highlight. So what you are trying to utilize in order to find out the mean squared errors would basically be, they would be two types of errors coming into the picture. So similarly, like the exponential moving average charts, one would be basically the differences of the variability where I am plotting. So this one which I am highlighting now, and that has been weighted by lambda. So this is basically the difference of the random variable or the realized values xi minus its mean value, square of that will basically give you an information that is something to do variability or dispersion. And the second part would be basically 1 minus lambda, which is the difference or the weightage which you have already given for the immediate reading, and along with that you basically multiply 1 minus lambda is basically the so called mean squared weights for the past data. So you are trying to give weightages like as you did in the exponential moving average method, like some weights you are giving to xi, some weights you are giving to zi minus 1, where zi minus 1 are the past data. So, this s square suffix I minus 1 are the past data error squares. So, the error squares basically would give us some information about the variability, that is why the word variability is used. It represents the in control or target value of the process standard deviation. We could plot an exponential weighted root mean square control charts also. In this case, obviously the main factor would be that we are trying to deal with the variability. So, if you are trying to deal with the variability, then remember that variability, considering the concept of our normal distribution comes into the picture, we will be using the chi-square distribution. So, which means the sample variance with respect to the variance of the population when you try to find out the distribution, the overall distribution which comes out to the chi-square with a certain degrees of freedom. So, that degrees of freedom would be dictated to what extent you have information about the mean value which is available, yes or no. So, if you consider the value of the upper control limit, so upper control limit is basically a chi-square distribution with degrees of freedom of, say for example, v, and this alpha minus alpha by 2 and 1 alpha minus 2 would basically mean to what side of the overall distribution you are looking at. So, you consider that if it is the both sided error you want to find out. So, the distribution, even though it looks like a normal distribution, it is not, it is a chi-square distribution. So, obviously there would be two errors, one would basically be corresponding to the values of chi-square v alpha by 2, another would be basically chi-square v 1 minus alpha by 2, such that the overall area which you have inside this one, when combined with 1 and 2, basically would make the total sum as 1. So, that means the overall coverage area of probability in under the distribution would be 1, which should definitely be. So, if you see the upper control limit and the lower control limit, they would basically be subject to the case that the chi-square distribution will be coming into the picture, because we are trying to compare the variability with respect to the standard deviation or the variance of the population. And as we know, as I repeated, that considering the distribution actually coming from the normal case, which is mentioned here, if you remember, as I mentioned, this x where my finger is, let xi be normally distributed. So, that is very important. So, once you consider that the actual base population distribution is normal, then obviously the distribution with respect to the variability would be chi-square with certain degrees of freedom, as I just mentioned. So, EWMA statistics can be sensitive to shifts in both the process mean and the standard deviation. So, obviously, because if you so I should spend about few minutes here. So, if you consider, say for example, there is a population and it is normal. So, and I need some information with respect to the mean, which is the first moment, or with respect to the variance, which is the second moment. Now, if it is only information with respect to the mean, that means in those cases there can be case 1 and case 2. So, let us discuss case 1 and case 2. I am just going to mention it qualitatively and verbally, and I am sure you will understand that. Consider the variance of the population is known. If it is known, the best estimate for the population mean value would basically be the sample mean value, which is, I will try to write it down, will be x bar n, which is the best estimate for the population mean, which is mu. In case of say for example, this will be true if sigma square is known. In case, say for example, sigma square is not known, still the sample mean is the best estimate for the population mean, and our work is done. So, in those cases, the sensitivity with respect to the shifts in the upper control, lower control, central line with respect to the case when we are studying the mean value of the distribution is not that much affected by the standard deviation. It would be in sample variance which is important, but in general the variance of the whole population would not be affecting that much. But let us take the second example or second case, where you want to find out something to do with the variability, which is sigma square. If I want to find out sigma square with the best estimate from the sample, there would be again two cases. Case 1 when mean value is known, case 2 when mean value is not known. In case mean value is known, obviously the best estimate would be 1 by n. I am just repeating the formula, 1 by n summation of in the bracket xi minus mu whole square, and we do the job considering the sample estimate to the best estimate for sigma square, and we complete our task and do all the calculation. In case, say for example, the mean value is unknown, then what is the logical step would be, basically we replace the expected value of the population or the mean value of the population with the sample mean, which is x bar suffix n. But as we are doing it, we lose 1 degrees of freedom, hence rather than dividing by 1 by n, we divide it by 1 minus n minus 1. Hence this new statistic, which is the sample variance, which is now the formula of 1 by n minus 1 summation of in the bracket xi minus x bar n whole square. So, this is the best estimate for the case when the population mean is not known. So, when you are considering the charts with respect to the variability, then obviously it would mean that the change in the mean value as well as the standard deviation would have an effect in how the overall chart looks like and how the values basically fluctuate or change. This suggests that the equation of the steady state, considering that both the upper control and the lower control would basically be the best estimate for trying to find out the upper control and the lower control limit for the variability EWMS charts, variability for the EWMS chart, which is for the variability charts for the considering the exponential weighted method is used. A logical estimate for mu turns out to be the ordinary exponential weighted moving average considering the standard form. They derive control limits for the resulting exponential weighted moving average or the variances considering the same method, like the overall square or error would depend on a lambda, which is the weights multiplied by the difference of the realized value minus mean value whole square, plus 1 minus lambda weights would be for the past data, as we did for the exponential weighted moving average, and based on that we do our calculations. Now consider that rather than normal we have the Poisson distribution. So, obviously very logically you would say that, well, Poisson distribution would be there, we will use that same mean and the same variance from the Poisson distribution, considering the central limit theorem, convert them into a normal distribution with the mean and the standard deviation coming from the Poisson distribution, and do our work. Well, that logical in a very practical sense is excellent. So, but let me also discuss further on. So, if x is basically a number of count, or as in the Poisson distribution is the discrete distribution, then the basic EWMA recursive method will basically be given by this. So, if you consider the same method which you have considered for the exponential weighted moving average, so Zi would basically be weighted by two things. Number one is lambda weights being going to basically xi, and 1 minus lambda going to the past data, which is Zi minus 1. So, with considering some starting value Z0 as mu 0, which is the central line or the target value, we basically recursively do that and do the calculation. So, if you concentrate here, so once Z0 is given, we will and is equal to mu naught, we will find out Z1 and multiply lambda into xi, which will be x1, plus 1 minus lambda into Zi minus 1, Zi minus 1, which is Z0 would be mu naught, and then we will find out basically Z1. Once Z1 is calculated, we will try to go and find out Z2. Z2 would be lambda into x2 plus 1 minus lambda into Z1, which we have just calculated, we will utilize that and recursively go till we find all the values. The parameters as discussed and exactly as we have done would basically be the central line would be given by mu value, which is this, and the values of upper control and lower control are almost the same, except the thing that this AL value and AU value are coming in the place of L, as we considered for the exponential weighted moving average concept. Here AU and AL are the upper and control limits factors. In many cases they are considered to be equal. So, again if you see, if you give them equal values, so which means that you are equally dispersing both on the positive side and the negative side. That means you are somewhere intrinsically at the back of your mind considering the normal distribution, which is equally dispersed both on positive side and the negative side. Positive side means more than the mean and less than the mean, negative side being less than the mean. There exist charts which show the values of lambda in A for particular chosen values of mu, and you can solve the problems accordingly. Now, how does EWMA work as a predictor of a process level? For an SPC viewpoint, the EWMA is roughly equivalent to the Kusum charts in its ability to monitor a process and detect the presence of ascertainable causes that result in a process shift. However, the EWMA provides a forecast of where the process mean will be at the next point in period. So, finding that is that Zi is actually a forecast of the value of the process mean at any point of time, say for example I plus 1, and basically you do it repeatedly till you are able to find out the best possible estimate. In computer integrated manufacturing system, where sensors are used to measure every unit manufactured, a forecast of the process mean based on previous behavior would be very useful. If the forecast of the mean is different from the target by a critical amount, then either the operator or some electromechanical control system can make the necessary process adjustment and do the things as required. If the operator makes the adjustment, then he or she must exercise a caution and not make adjustment too frequently, because this will actually cause the process variability to increase and have a negative impact on the overall statistical process control method which you are trying to utilize. The control limits on the EWMA charts can be used to signal when an adjustment is necessary and needed, and the difference between the target and the forecast value of the mean can be used to determine how much such adjustments need to be made, both on the positive and the negative side. The EWMA can be modified to enhance its ability to forecast the mean. Suppose that the process mean trends or drifts steadily away from the target. The usually EWMA equations can be written by again the same concept. So, you give a weights of lambda to xi and 1 minus lambda to zi minus 1, and you do the calculations accordingly such that you are able to find out zi values. In view of zi minus 1 as the forecast of the process mean in period I, we can think of xi minus zi as the forecast error. So, this is what is important. So, say for example, you are trying to find out the errors. So, technically errors would be, as we know, is xi minus xi hat. Hat is basically the predicted value of xi. So, if you consider this xi hat to be zi, so what you are trying to do, you are trying to find out the difference between the actual value, and let me change the color, the predicted value. So, this is on the same scale. So, if I find out the difference, this value is epsilon, this area, this epsilon error for ith time period would be weighted by lambda, and we will do the calculations accordingly. So, so zi would be found out by zi minus 1 plus lambda weights going to the errors, which is epsilon I or ei. Thus, the EWMA for a period I is equal to the EWMA for period I minus 1 plus a fraction lambda multiplied by the error term. Now, if we keep adding up, you will basically have the error for time 2, time period 2, time period 3, and so on and so forth. So, this is basically a recursive series, and you can find out depending on the properties of the assumptions which is there for the errors. So, obviously, in many of the problems the errors concepts are given, and you can solve the problems accordingly. So, where now considering that if there are more than lambda is changing. So, if lambda is changing, technically the errors weightage would be changing. So, if you see this equation which I am trying to basically highlight now with the green color. So, basically we will have the error of period 1 multiplied by lambda 1, error of and j would basically be all the sums of the errors starting from 1 to I to that period. So, we can basically sum them up and find it out. So, this factor of delta would basically be the difference of the error for time period 1 and time period 2. So, the EWMA is in period I obviously would equal the current estimate of the mean value plus a term proportional to the error plus a term related to the sum of the errors, and it will be done recursively from time period 1 to time period 2. So, these three terms can be thought of a proportional, integral and differential adjustment, and you will find out how we can find out. In one case it is the actual value, one case is the sum value, one case is the difference value. The parameters of lambda 1, lambda 2, lambda 3 would be chosen to give us the best results. So, with this I will end the 39th lecture and just wrap up the TQM course in the 40th lecture and give some details about the importance of total quality control and its consequence in our daily life. Have a nice day. Thank you very much.